Hi, welcome to the Signal Path. In this episode I have another product review for you guys. We'll be taking a look at the Keithley 2460 source measure unit. A short while ago I did the review of the Keithley 2450, which was the brand new replacement of the 2400, and it had the touch screen and the new GUI interface, which I really liked, and I did an extensive review of that. The 2450 is a precision instrument and has a very low noise, high sensitivity, which can provide very small amounts of currents and voltages, but it maxes out at 1 amps, and as a result it is not suitable for some high power applications. The 2460 is supposed to address that. It is basically on the same family as the 2450, it's on the same footprint, it looks exactly the same, but it's capable of delivering or sinking up to 100 watts of power and up to 7 amps, making it much more suitable for high power semiconductor experiments. So the combination of the 2460 and the 2450 is very powerful because it can cover a much broader range of applications that you couldn't do before, and that's what this review is based on. So make sure that you watch the review of the 2450 to be familiar with some of the stuff that I talked about then, because I'm not going to cover them again in this video, giving us more time to do experiments. And I cover, again, starting from simple experiments, slowly getting more and more complicated, looking at the scripting, looking at KickStart, application that can be used with these instruments, and do a whole bunch of really interesting things. And together, between these two, hopefully we'll have a complete view of the new Keithley source measure unit. So let's get started. So as I was saying before, the form factor of the 2460 is the same as the 2450, even though it has a much higher power dissipation capability. So I'm interested to take a quick look inside of it, just so we can examine how they've managed to put all those inside the same unit size as the 2450. So I'm going to just take this apart. Again, it's very easy to take apart. I'm going to skip that on video, but these panels come off, these rubber feet come off, and then there's a bunch of screws you take it off, and I assume then the top will slide off. So let me go ahead and take a look. Here we are looking at the bottom side of the instrument, and you can clearly see that this is a very modular design, as to be expected from instruments like this, where they reuse different sections and components for other type of instruments in the same class. So here at the bottom, this is clearly the PCB that handles all of the digital processing. The OS runs on this. All the IOs are handled here. You can see at the back all of the GPIB, the Ethernet, the USB, and the serial port. They're all connected directly to this board. You have some application processors on it, the buzzers on here, Spartan 6 FPGAs on here. A little battery to keep the BIOS settings is here, as well as a couple of connections to the front of the instrument. There's also some not occupied things here, which I'm sure are used for who knows what, perhaps during manufacturing or some other options that are not available here yet. Some DC-DC converters go on here, and there's an interesting way of connecting this PCB to the main PCB at the bottom. They have this little board design where the edge of this PCB plugs into this edge connector, and the other side of this PCB plugs down into the other PCB. So you have this 90-degree transition done this way by using two of these type of connectors. At the center is a very large shielded component. Now there's several components underneath here, some sensitive EM sensitive components for measuring perhaps, or some reference or something, I'm not sure. This doesn't come off, and you can see some 50 milliohm resistors on this board on this side, some optocouplers and so on. Other than that, nothing that stands out that's surprising. This ribbon cable directly drives the front panel interface. Now the thing about the LCD screen of this particular unit is that it's completely standalone. It has its own processor, it has its own FPGA, and everything is handled directly through this ribbon interface. And when you upgrade the firmware of this, you don't just upgrade the firmware of the components here, you actually also upgrade the firmware that runs on the display. This allows them to use this display essentially for any of their new lineups of this GUI-based instruments. The new multimeter that are released, the Keithley 2450, the 2460, they all use the same interface. And it's nice because you can keep upgrading it and have a consistent UI across all your platforms. And I'm really looking forward to that. Keithley is doing a really good job on that. And here is the main power supply of the unit itself. This is the power button here. You can see that it travels from here, goes down in there where it's connected to the back of the unit here, and underneath where the power switch is. On this side you cannot see anything, but if I were to flip this a little bit, before I flip, Here's some ferrite cores here for some filtering. Some wires loop around here, perhaps to get rid of some transient effect or to protect the instruments inside from seeing very, very large voltages due to some current spikes. So there's some filters that have been designed there. And if I flip it a little bit to this side, you can see between the two boards, there is a lot of capacitors, just banks and banks of capacitors in here. There's some components here which either are rectifiers or transistors, and these capacitors, you can see a bunch of these actually footprints that are not occupied with anything. I'm not sure why they haven't been installed, those capacitors there, but this instrument supports, just like the 2450, different states when the power is disconnected. When the output is disabled, you can have high impedance, you can have connected to zero, you can have low impedance and so on, and I'm sure this uses some of these capacitor banks. Here's a voltage reference here, what appears to be, and there's again a bunch of components on the other side. If I were to flip it, you can see how they are handling the thermal issue of this board, which is going to be very interesting. So this heatsink is clearly the heatsink that has all the power transistors on it. So this is the main heatsink which will dissipate the 100 watts of power that the instrument is capable of delivering. And look at all these nice cutouts inside the PCB for isolation and for ensuring that everything is well characterized and so on. I'm not sure what's on the other side. I'm trying not to touch any of these things because again, this is a calibrated unit. Look, some cutouts of the PCB here. Very interesting, just because these capacitors are just a little too tall, I think, and they want to make sure that they don't make contact with the other side of the board. Very nice. I can see the power cable, the power from the front panel goes all the way in to support the rear panel, because you can again connect from both sides, so these cables are intended for that. And there's a really big fan, this turbine style fan, which blows air directly into here. So I suspect this is going to be rather loud, but again, that's a decision they've made in order to fit this into this size here. There's some empty space here, but the loudness of the unit is going to be a compromise between the size of it and of course how much power dissipation you can have. So, you know, that's to be expected. And you can see at the bottom here some components of the power supply, main power supply of the unit. Otherwise, it's very, very nice. Again, to be expected from Keithley, nothing out of the ordinary, and this is a very, very complex, very compact unit that they have built, and obviously they've done a really nice job here, and everything is tied down, all the cables are tied down. I don't see a lot of glue on the bigger capacitors. I guess they don't really expect this thing to bang around very much, but so far it seems nice and solid to me. Again, everything is tied down here, a lot of cables running around, but things are nicely taken care of. Even these small cables, they made sure everything stands, and there's a shield on top of this plastic shield so it doesn't make contact with the case. These guys know what they're doing. I'm not surprised to find really high quality. So I hope you like to see what's inside it. I'm more excited to run some of the experiments. So let's go ahead and run some tests. So what is the difference between the 2450 and the 2460 in terms of their power envelope? So here I have both of the plots, and the 2450 power envelope that I've shown you from before, you can see that the unit is capable of delivering up to about 1 amp of current, about 20 volts, and then once you go to 200 volts that drops down to 100 milliamp. But the range is very large, from plus and minus 200 volts and plus and minus 1 amp. Now the power envelope of the 2460 is much more complex, and it's a 100 watt instrument. So as a result, it's actually able to give you plus or minus 1 amps at plus or minus 100 volts. But once you get closer to lower voltages, for example, at 20 volts, you can have up to 4 amps, and at 10 volts up to 5 amps, and at 7 volts up to 7 amps. So you can have this complex power envelope, and you can operate in different regions, these rectangles, depending on the voltage requirements of your instrument. So you can see that this is a much higher power model compared to the 2450 from before, and that is one of its main advantages. So if I were to just do a very quick comparison, you can see that the main difference really between the 2450 and 2460, aside from the current consumption, is that the 2450 focuses on very low current and voltage measurement and delivery capabilities. So it's a more of a precision, very low noise instrument, very high dynamic range, and the 2460 essentially moves that dynamic range of voltage 1 decade up in order to be able to achieve everything that it does. And everything else is pretty much the same, and I suggest that you go ahead and look at the data sheet, a full specification of the 2450 and 2460, to find out which ones is more suitable for your application. Of course, one of each combination will be the most powerful for characterizing multi-terminal semiconductors. And I'm not going to go into too much detail because there's a lot of experiments that I want to do, but I wanted to just briefly touch upon this and make sure that to point out that you should take a look at the datasheet for more information. Even though it's not really necessary to verify the performance of these Keithley meters, after all, these are Keithley instruments rated to 6.5 digit. I'm sure they meet their specification. No reason to dig into that. It's more interesting to do other tests on it. But I do want to show you something that I've picked up recently, which might be interesting to do a quick measurement with. This is a voltage standard from voltagestandard.com, and the people who designed this, when I purchased it, they automatically upgraded my order and gave me an enclosure and also to the next better voltage standard that they have to offer. So I'm very thankful for that. So definitely check them out. This little box gives you DC voltages, AC currents, AC voltage, and resistor standards on the side, and it comes with a calibration certificate which tells you exactly what those measured values are with a very high precision and NIST traceable, and also with the serial number of the instrument that was done. Everything is there. You can send it back for recalibration to them and so on. So we have some of the basic measurements. We can do just a quick test. For example, the DC voltage is 5.0000 is what it was calibrated to. So we can go ahead and quickly try to measure that. So I'm going to connect this to the 2460. We're going to connect to the negative terminal, connect this to the positive terminal, so on. And I'm going to connect that to the voltage reference here off camera and to that little box. And I've turned it on, let it settle down for a bit. And there it is. This is what we get. We're going to let it filter a little bit because this is on filtering a bit. And look at that. I mean, that's as good as it's going to get. There it is. Almost all zeros. This actually has an extra 0 compared to what the calibration certificate had. The calibration certificate has only 4 zeros, so this has a bit more. Again, the temperature in the lab isn't exactly the same as the temperature where the calibration was done on this box. It's a bit warmer, so the temperature is going to be a little bit off from the calibration, but as you can see, it's very, very close. We can also do the same thing at the with the 2450, and again we have to wait until it settles down a little bit. There you go. So this reads a little bit higher than the other one, but again, you just wait a little bit and it will hopefully settle down. So it's all accurate. Again, I have no doubt. I just wanted to show you this voltage reference, and we can measure everything else. But I've tried it all out, and it's all within specification. No worries there. So the Keithley 2460 is capable of providing very high currents, but not just at DC. It's also able to provide very high sharp pulses of current, and I'm going to demonstrate it as our first experiment. I have written a code to program the 2460 to output narrow pulses of 1 millisecond, pulses of 6 amps of current for a certain number of repetition. Now, that's by no means the minimum value. You can even reduce it below that, and what I wanted to do is I want to show you a measurement of the pulse currents that the 2460 can create. And in order to do that, I've just put together something very simple. This is a 1 ohm resistor across the 2 terminals of this banana plug essentially, and I'm going to put that at the output of the 2460 like so. Now basically what's going to happen is that the current is going to go directly through the 1 ohm resistor, create a voltage across it, and that voltage is going to be proportional, of course, to the current. And since this is 1 ohm, you're going to get 1 volt for every 1 amp. And I'm going to go ahead and connect an oscilloscope probe like so. Oh, let's go the other way. Oscilloscope probe like so across the 2 terminals, and now we can measure the pulses of current that are coming out directly out of the 2460 like this. And now remember that I've chosen this connection to be very short because I don't wish to have any inductance in that, because I am going to be pushing 6 amps of current with very, very narrow pulses, and if you have a lot of inductance you can actually create very large voltage across them, so you want to avoid that. And in order to measure it, I have set the Tektronix MDO to basically collect the currents, and I'm going to run the script once, and this is in a single capture mode right now, so we will be able to see the pulses of current. So I'm going to go ahead and run the code, and this is on single capture, so we should be able to see the pulses. There we go, and this is just a few of the pulses that I've captured here. Now remember I said that the pulses are 1 millisecond in duration, and indeed they are. So now we're at 1 millisecond per division, and you can see that's exactly how much this is. This is 1 volt per division, so 1, 2, 3, 4, 5, and 6, and exactly 6 amps, and for a duration of 1 millisecond. Now if I go ahead and zoom in further, you can estimate roughly the rise time here of this pulse is in the order of 80 microseconds. So it goes from 0 amps to 6 amps in about 80 microseconds or so, about 10% to 90%. So you can see that it does have a very, very rapid rise time, and this is also true for the fall time. Now, of course, there's some capacitance discharge that needs to happen, and you can make these pulses even narrower if you want to, but this is a very useful feature if you want to investigate pulse effects on some type of a semiconductor or some kind of circuits. So it's not just the DC value power providing the 2460 that has been improved, it's also the pulse generation capability. And I just wanted to show that very quickly before we get into our main experiments, because it is an interesting and useful feature of these units. So there is an aspect of the performance of the 2450 and the 2460 that I want to show you before we get into the main experiments, and that is when these sources drive a load that has a very erratic transient response. And that's something to keep in mind, and I'll explain to you how that works. So here I'm running a really small brushless fan, and you can see that it is spinning, and it's actually quite noisy. It's not a very good fan. So it has the ball bearings inside have a little problem, so it occasionally catches, and it has a very random behavior as a result of that. And of course, as with any brushless DC motor or even brush DC motors, there's going to be a lot of spikes of current when you run this. Now, here I have the 2450 supplying set to 7 volts, a current limit of 106 milliamp, and a current measurement range is set to auto. But as you can see, even though the voltage is set to 7 volts, the instrument is not supplying 7 volts. It's supplying about 6.6 volts, and there's some variation around that point. Now, normally, if you were in current limiting mode, the instrument will tell you that you're in current limiting mode. The display will turn yellow, and the word limit will be shown here. But it is not doing that. It's not telling you that it's limiting. Now, the reason for that is the following. The instrument is receiving very sharp and narrow pulses of current because of the operation of the fan. Now, those pulses are caught by the analog circuitry inside the unit, which automatically will adjust the voltage. So internally, the analog circuitry will ensure that the current limit supplied to the source will never exceed 106 milliamp. But if those pulses are really, really narrow, the digital circuitry that monitors and displays the limit will ignore them. And as a result, the instrument is supplying an average voltage of about 6.6 volts, which doesn't cause the whole system on average to go over the limit of 106 milliamp. So it's doing exactly what it is supposed to do, except that it's not showing the limit. Now, I've spoken to Keithley about this, and their engineers are extremely responsive, and I appreciate that. And they said that they're considering even implementing a way for the user to set the digital monitoring of the limiting factor, so you can tell it how quickly it should react to the limiting factor by showing the limit here. Now, they haven't promised that they're going to do this, but that's something that they're considering, and they're aware of it. But if you run into a situation like this, it's quite easy to fix that. You can just, for example, change the automatic measurement of the current to a higher value. Here, let's set it to 1 amp. And now you can see that because it doesn't have to switch range anymore, it can catch the limiting much more often. Now you know that, oh, you know what, I'm sometimes in limiting mode, so I can go ahead and increase my maximum current limit. For example, let's set it to 1 amp, and there it is, and the problem, of course, goes away. Now, those pulses are still there, and this number is this instantaneous measurement doesn't include the peak currents that go through, but now it's able to supply the proper amount of voltage. So that's something they're working on, and it's something for you to keep in mind whenever you're going to run a transient inductive load that has a high spikes of current going through it. So now that we know that it does this, we can do some really unusual experiments with this. So let me set that up, and I'll tell you why, for example, it would be useful to be able to adjust the timing of the monitoring of the limit current with a quick example. So here I have a Geiger counter. This is a Ukrainian pancake style counter, and the reason they call it a pancake style is because of its flatness and the shape of the mica opening window that is on top of it. Now, a Geiger counter is filled with a low pressure inert gas, and normally it has a very low conductivity between its two high voltage terminals. And as soon as a high energy particle like an alpha or beta particle enters the window and enters the gas, it will ionize the gas and release electrons. And the electrons will then create conductivity inside the glass. But there is more to it than that, because that process has an avalanche effect, and that ionization, it would create a cascade of ionization particles and then increase the conductivity very, very quickly. It would create an avalanche of current. Now, as soon as that happens, the conductivity will shoot up significantly. And of course, you don't want to stay in that mode of operation.
and under that case normally you'll have to immediately drop the voltage below the ionization level, and then the process will stop and the conductivity will once again drop, and then you have to raise the voltage back up again. Normally this is achieved by having a very large series resistor with a Geiger counter, because normally the conductivity is low, so the drop across the resistor is not very significant. And as soon as the avalanche effect takes place, there will be a huge drop across the resistor. We'll take it out of the avalanche mode and then reset the tube ready for counting another particle. So now this particular tube requires about 300 volts to operate, so now we can actually operate this from both of our source meters. So let's go ahead and see how we can do that. Here at the very top I have the 2460 set to 100 volts, which is its maximum voltage, and I've set it actually to 1 amp because I don't want the 2460 to do any limiting for me. I just want it to be a very steady 100 volt supply. Now at the bottom I've set the 2450 to 200 volts, and I've set its current limit to 20 nanoamps. So as soon as the current goes above 20 nanoamps, the 2450 will go into limiting mode, will drop the voltage rapidly to account for that, and then it will bring the tube out of basically the avalanche mode. And these are in series. You can see I've had a series connection between them. They're of course all isolated power supplies, so you can easily put them in series. So the voltage across these two terminals will therefore be the sum of these two, be 300 volts. So I can go ahead and turn it on, and then we'll see the conductivity when there is no particle present. There we go. We can turn both of these guys on, and there it is. Now everything is stabilized, so you can see that at the bottom one is sitting at 200 volts, the top one is sitting at 100 volts, and the conductivity of the tube right now is 0.6 nanoamps. It's essentially nothing. And of course the tube is just sitting steadily, nothing is really happening. There's not that many radioactive particles in the lab, I hope not. And now we need is some kind of a radioactive source. So here's a radioactive source, and this is a gas mantle, and if you're older or if you've come from a country that's been at war, you probably recognize these because we used to use these when the power would go out, when the electricity wasn't available. And so what this is that these gas mantles were used to create light from a natural gas source by putting natural gas directly through them, burning the gas, and then these guys would glow. And now you may ask why that is the case. Well, these things are actually laced with rare earth oxides, this particular one with thorium dioxide. And the reason they use that is because these rare earth oxides have a very high emissivity in the visible range. So unlike some of the other materials, when you heat them, they don't emit as much infrared light as they do visible light. And of course it's visible light that you're interested in because that's the one you can see. Nowadays they use other types of rare earth oxides which aren't as radioactive, but thorium dioxide is radioactive, and therefore we can use this as a source for our alpha and beta particles. And even though this is in plastic, some of the particles will still escape. Normally this is not dangerous. It's mostly dangerous in manufacturing, of course, if you eat it. So as long as you don't do those, these things are fairly safe to handle, and they have very low amount of energy anyway. So let's go ahead and take a look and see what happens. So right now you can see that both of these sources are not doing anything, and I'm gonna bring this lantern on top and look at that. You see that? You see how the unit will continuously jump into a limiting mode, and I'm going to move away. There you go. I'm going to have it up here, and I'm going to put it right on top of the tube again, and there it is. And you can see that we are catching the radioactive particles, and the unit is reacting to it. And I can go ahead here and actually plot it, and there you go. You can see it catching this. I'm going to move it away. I'm going to bring it back down. And there it is. So the reason I did this experiment is because I was interested in seeing if I can make a Geiger counter directly from the source meters, and I think you can. It's just a matter of being able to set the timing of the limiting being detected. And if you can do that, then you can actually count the particles and write a script to go ahead and do that. So I'm excited to see if they will implement this functionality that the user can then choose the limit and then therefore catch the particles. So if I hold it up here, it's not going to catch many. As soon as I bring it down, you can see there will be many of these particles being caught. So it's a very unusual little experiment to do, but nonetheless it will be very interesting, and I'd be curious to see if they will decide to implement this functionality.
So let's do a simple test here. Sometimes it's interesting to investigate the failure mechanism of a particular component because you want to know if the component fails in a consistent way. You'd be surprised how much information you can get from a semiconductor type of circuit by looking at its failure mechanism. So here I have a whole bunch of white LEDs that I bought a while ago, and I'm going to sacrifice these ones for science, and we're going to investigate if they all fail in exactly the same way. Now, sometimes to stress and look at failure patterns on semiconductors, you will need a very high power instrument. And of course, this is where we have the advantage of the 2460 because it can supply so much more current. So I'm going to try a failure mechanism on these LEDs all the way up to 10 volts and up to 5 amps. And of course, these LEDs are going to fail long before that. And we're going to use the KickStart software, which I'm running here on my laptop, and I'm going to show you a screen of that separately. And we're going to run multiple sequences where we basically sweep the voltage across this diode. There's one right up here across this LED until it fails, and then we're going to have a graph of that, and we're going to superimpose the graph of all of these, and then we can actually clearly see not just the IV characteristic of the LED, which is exponential as to be expected, but also we're going to get to see if they all fail in exactly the same way. And that will be a little interesting and a simple experiment to do, and that we get to use the KickStart software for that. So let me give you a quick overview. Again, if you're watching this, make sure you've watched a review of the 2450 first, because this is really a complementing that other review that I've done, and where I talk more in detail about this. But you can quickly see how I've set up this software. I apologize for filming the screen, is because I need to move the camera around. So again, because these instruments are connected at the back together with the TSP interface, both of the channels of the source meters appear here. So channel 1 is the 2450, which I've disabled in this test, and channel 2 is the 2460, which I've set for just a voltage sweep, very simply between 0 volts to 10 volts with 0.1 volt steps, and a maximum current of 5 amps with a 0.5 250 millisecond steps. Everything else is really straightforward. I'm measuring the voltage, and then it will record and save everything for me neatly in tables, which then I can collect and put into a different software, or I can just plot directly in here. So I will film once the failure of the LED, once the screen on the source measure unit, and then of course one time with the live plotting of this. But I'm sure you want to see the LED failure, so let's go ahead and look at that. And in order to do that, I'm going to put this little cup, or glass I should say, directly on top of the LED, and I do that because I'm not sure how it's going to fail. It may pop and pieces may fly around. I'm wearing a goggles anyway. Never take any chances with these things, because again, if something happens, it's irreversible. So let's go ahead and run this software. So all I need to do just to come in the corner here and just press the test, and then it's going to start sweeping. So now it's doing that, and we can take a close look at the LED, and it should soon light up as the voltage goes up. There it is. Now it's 2.7 volts. It's 18 milliamps, 70 milliamps now. There you go. Now it's over 200 milliamps at 5 volts, and almost, oh, it's interesting. There it is. Oh, and look at that. There we go. So you can see now that it completely failed, and you had a couple of shorts and opens in between. You can see it's still sparking. All right, let's do another one. There we go. Run it, and we can see, just to take a quick look here at the plot, at the instrument, you can see clearly that the voltage is stepping up. It's already over 100 milliamp, and of course you can always plot this directly. Oh, going the wrong way. You can always directly plot it here. You can see, oh, there it is. You can see that that was a failure point, and actually 2 steps. So it, and you can see it actually does this very interesting thing, and I think this is rather repeatable too. So here the current goes up, and then it fails once, and then there is a thermal effect where the connection collapses back together, and you get another spike. It burns up, expands, and collapses back together, and one more time, and this is a failure mechanism. Just by looking at the plot, you can see, we can conclude that. So I'm going to go ahead and run this many times and destroy all these LEDs so that we can get a collection of plots and see it, put them all together, and you can actually see the graph here too. There it is, the same graph that you saw on the screen. It's live being assembled. And here's the result of all the failure study. And there's some really interesting behavior we can observe here. You can see that, of course, the region in which you want to operate the actual diode is just only in this area. this is the region where you want to be in, because this is less than 10 milliamps. And even here there is some variation between the diodes, but only within a couple of milliamps would you ever operate a component like this. And you can see that the bias voltage is about 2.6 volts. Above that, you're beginning to damage the LED, and here is already quite bright. So this is where the normal operation of the LED ends, and the whole graph shows some strong correlation between how the device fails and how it behaves after it has failed. So you can see that the current moves away from the exponential rise to a more of a linear region here, and then it collapses very rapidly, and then after it cools down a bit, you can see a few spikes of current in here, where we saw also on the instrument while we measured it, you could see the sparks from inside the LED, and that, I believe, is the thermal effect. Now we should also keep in mind that this behavior will depend on how fast we raise the voltage, and so it's going to have some correlation to the step size between the points of the sweep. But of course I'm here only comparing them together, so I'm only interested in the relative difference, but you can see some consistent behavior. So a study like this in an LED is interesting, but can be very, very helpful when you want to characterize or qualify a particular device or IC, or even something more complicated where you want to study what type of failure mechanisms you can have. And this was so easy to do because the KickStart software, which is in the background here, makes it really easy for you to collect data and then move them onto a spreadsheet and then investigate what happens to them, and it's very, very straightforward to use. And I'm glad to see that Keithley is making a unified interface for all their instruments, because if I go under here on the left side, you may not be able to see very well, but they support various types of measurement like data logging, precision multimeter, and precision DC power source, which are their other instruments which they have recently released. So it would be interesting to take a look at those as well. But for now, that was I think a cool little experiment. I'm not sure if anyone's ever shown this before. I'm sure it exists somewhere, but pretty cool experiment. So for the next experiment, I'm going to program the Keithley 2460 and the 2450 to act like a programmable transconductance stage. Now, what do I mean by that? Well, sometimes you're designing a particular semiconductor that has some IV characteristic that you want to investigate. Now, you can program that IV characteristic directly into the 2460, 2450 without having the semiconductor finished yet. This allows you to investigate a wide range of transfer functions, IV transfer functions, from a device before you even have it ready. So what I'm going to do is I'm going to program the 2450 to monitor a voltage here, and I'm going to allow a particular equation to define the output current of the 2460. So in this case, the 2460, 2450 would be like a transconductance of a transistor. So I can program, for example, a quadratic response which will simulate a CMOS transistor, or an exponential response to simulate the bipolar transistor. And of course, I'm not limited to that. I can do nonlinear, I can do segmented linear, I can do a lookup table, I can do pretty much anything I want and create a really complex IV characteristic between these two instruments. And this can be extremely handy. You can also do something like having the 2460 be a voltage follower to the 2450 that then can supply much more current than the source that you want to actually follow. Let's say you have some voltage coming from a transistor that has only a driving capability of, let's say, 1 milliamp, and you want to multiply that by a factor of 1,000 and drive 1 amp. Well, you can program the 2460 to follow the 2450 in exactly that fashion. So here what I've done is that I have programmed with this scripting capability to ask the user for the transconductance coefficient and the polynomial degree, and then be able to output that here. So the 2450 is simply connected to my Rigel power supply here, so I'm just putting a voltage directly into it as my voltage to the input of the 2450, which would go into the equation, and then the 2460 at the top here is connected to this halogen lamp, which is a very tough load to drive, not just because it requires a lot of current, but also because its response is heavily time dependent due to thermal reasons. So at the beginning there will be a big inrush of current, and then the voltage will rise up as the filament gets really hot. So this is a difficult load to drive, typically with a type of solid state devices. So we're going to basically drive it using these two combinations, and once I run the code, it'll become much more clear exactly what it's going to do. Alright, let me initiate the code from the computer here.
There it is. So what it's first doing is asking me to enter the transconductance coefficient. So let's go, enter something, I don't know, reasonable, let's say 1.5. And then it's going to ask me for enter the transconductance polynomial degree. Again, I've programmed into this so you can program anything you like. So let's say we want to simulate a quadratic equation, so that will be to the factor of, to the power of 2. And let's go ahead and click OK. And now it's telling us, okay, so the response you're looking for is I, the current from the top unit, will be equal to 1.5 times V to the power of 2 amps, which is the voltage monitored here. So right now the measured voltage is 0, therefore the supplied current is also 0. It's also going to measure the voltage across the terminals of the 2460. So now I can go ahead and, for example, increase the voltage here slowly. So I'm just going to go up by 0.1 steps, and you can look here to see what happens. So again, it's measuring the voltage live. So let's go to 0.1 volt. There it is. Now you can see it's measuring 0.1 volts. So now it's sinking 20 milliamp because 0.1 to the power of 2 times 1.5 will be equal to that number. So let's go ahead and increase this a little bit more. So 0.2, you can see that it's following a quadratic response. Let's go to 1 volt. So at 1 volt, what do we expect? Well, 1 to the power of 2 is just 1 times 1.5. We're going to expect 1.5 amp, and indeed it's 1.5 amp. Even though I'm putting 1.5 amp in the halogen tube here, nothing is happening because it's not enough to create any significant voltage across. And you can see the voltage across that is slowly rising is because the halogen filament is getting hotter. Now, what is important to note here is that, of course, there is absolutely no power being delivered from the Rigel supply, because the Rigel supply is only supplying a voltage to the input of the 2450, which is a high impedance input, just monitoring the voltage. All the current is coming from the 2460. So let's go ahead and increase this to some higher value. Let's go to 1.5 volt. There it is. So now at 1.5 volt, we are beginning to see the halogen lamp light up. And now the voltage across the lamp is now at 5.25 volts, and the current going is 3.38 amps, which is what the equation will dictate. And if I keep increasing it, if I go to 1.6 volts, for example, you can see that the voltage across it will go up significantly, and the current goes up, and now this is much, much brighter than it was. And now you can hear the fan of the 2460 go because it's delivering so much power to the halogen lamp. So this is a very simple and quick experiment, and look, even though I'm burning 3 amps right there through the diode, through the halogen lamp, there is no power, of course, delivered by the Rigel supply, and this is what the whole point of the transconductance is. So the transconductance equation between here and here is given by that. Now, of course, depending on how fast you want to run this loop, it's going to run into the limitation of the interaction between these two units, but you can program this to indeed respond very, very quickly and have even some transient response from this, even though it's meant to be more of a DC characteristic. But nonetheless, we can see how easy it is to program some complex equation between these two units and get some really interesting IV characteristics. Now you can go ahead and put this in your system and actually investigate what would a characteristic response like this have an impact on your overall system before you go ahead and design a semiconductor.
For our next experiment, we were going to characterize a voltage regulator that I have built here in the lab. This is a really simple voltage regulator, and it comprises an op-amp, MOS transistor, and just a dummy load 1 kilo ohm resistor here. And the way this circuit works is that the op-amp is in negative feedback between the gate and the source of this power transistor at the output. And because the open loop gain of the op-amp is very large, by applying a V reference to the negative terminal, the op-amp will then adjust the gate voltage such that the source voltage will become equal to V reference, with whatever difference between those two will depend on the open loop gain of the op-amp. So this is a very common way of building a voltage regulator. And of course, when you build a voltage regulator, there are several really important parameters that you want to keep in mind. What is the dropout voltage? What is the load regulation accuracy? How much current can I provide? How fast does it react to transients? A whole bunch of different things. Normally, a IV characteristic of a voltage regulator like this will be done in 2 dimensions, which means that it will sweep the output desired voltage versus output desired current, and you will get essentially a 3-dimensional plot telling you the performance of the voltage regulator across all of the voltages. So here, what we can do is that because we have now the 2460, which is capable of delivering up to 100 watts of power, we can use that as a dummy load for our voltage regulator, which then it will basically absorb the current from the regulator at any desired amount while we power the V in from an external power supply. And we can also use our other SMU, the 2450, as our reference voltage for the op-amp. So by using the two 2450 and 2460 in this configuration as a V reference and a load, we can do a complete characterization of a voltage regulator. And even better than that, we're going to use the scripting features in order to do our two-dimensional sweeps and do all of our plots and all of those wonderful things. So I'm going to show you. So now that you've seen the schematic, let me just give you a quick look at the setup, and then we will run the experiment. So here's my lab-made, homemade I should say, voltage regulator, which has a big heatsink and a fan on top of it because we want to be able to dissipate quite a lot of power from it. So let me just give you a quick closer look at this. Again, like I said, it's very simple. You can see on this side, we can see the power transistor tucked away inside the heatsink, and we can see our op-amp right there. So this is basically the schematic that I showed you, and on this side is where I'm applying various voltages and taking the power supply voltage and the output voltage out. And I will explain more of exactly how the setup works. And as I said, we have to be careful when we take voltage in and out of the voltage regulator because we don't want to have any IR drop across our cables here. So what I have done is that I have made these makeshift 4-wire testing fixtures here. You can see the two wires come here together, so I'm monitoring the voltage of all the cables right here just before the connectors. Of course there's going to be some more IR drop across these connectors, but we're going to ignore that for the purposes of this experiment. And normally you're going to have some IR drop anyway on your PCB, so this is not completely unrealistic. And here you go. So we have the Rigol power supply over there, which is the main power supply, which is going to provide the main power for the regulator itself. And then we have our two source meters here configured as the following. So the bottom source meter, the 2450, is going to apply our source, our reference voltage to our regulator. So whatever voltage this guy is going to set is going to be the desired output voltage of the regulator. And the 2460 at the top, which is set in 4-wire measurement mode so that we don't make a mistake on the IR drop on the cables again, is going to be our dummy load. So this is going to absorb current from the regulator and tell us basically what voltage it is reading based on how much current is taking. So basically like a precision load. And because they are connected together at the back with the scripting capability, we are able to run this whole test in one sweep and get a complete two-dimensional monitoring of the performance of the regulator. Now at the same time, at the very top here, I have the Siglent STM3055A, which I'm using just to monitor the gate voltage of the regulator. So if you remember, there is this voltage here which is going to be adjusted automatically by the op-amp, and it's going to be monitored here by this Siglent one. This is just to have an eye on it, just to make sure that everything makes sense. It's not really necessary as part of this test. So based on this, we're going to go ahead and run the script, and you'll see what I've done with the script and what it does on the instrument. Let's go ahead and enable our voltage source here. There we go. And you can hear now the fan that I have installed on top of the regulator go. And the reason, of course, because if I don't have the fan, the transistor will eventually heat up and burn up, because the linear regulator, even though is extremely accurate and it's very low noise, it's not very efficient when it comes to power dissipation, because the difference between the voltage that comes into the regulator, here you go, actually let me show it to you here. The difference in the voltage between V in and V out is going to be dissipated depending on the current directly on the transistor. So you have the lower the V out is with respect to V in, the higher the power dissipation in the transistor, which of course I'm going to sweep the V out all the way from close to 0 and all the way to close to V in. So we're going to go through a wide range of power dissipation in the transistor, and that's why the fan is necessary. Here we go, everything else is already set up. I'm going to run my script here from the computer, and then you can see the screen. Here we go. There you go, it started. So it's going to take care of everything automatically internally, and I have some messages being displayed here. So let's take a look. At the bottom, you can see that I'm saying that the regular reference is right now set to 1 volt, and at the very top, I'm mentioning what the set current is. Right now it's at 3 amps, and at the very bottom here I'm calculating the regulation error. It's because obviously because these two are connected with the scripting TSP from the back, they're aware of each other's settings, so I can program them to know what the other setting is. So the top unit knows what voltage I expect from the regulator and therefore can calculate for me the regulation error based on the voltage it's measuring at a particular current. So you can imagine this two-dimensional sweep is taking place, but I continuously change the reference voltage, and then for every reference voltage I change the desired amount of current that I sink from the regulator, and I calculate the regulation error. And when this is all completed, the program will then return to us a large table, a two-dimensional table of all the values it has measured. And actually you can begin to hear the fan inside the 2460 just went on. Remember that this is a 100-watt total power can be dissipated. I'm not doing that right now, but it can do up to 100 watts. So it has a really large fan, as you saw. There you go, now it's at full speed. So like I said, it is a little bit loud, but personally, to have this unit to be the same size as the 2450 in the same footprint, I think it's a reasonable compromise to make. So there you go. So this is going to run for some time. It's pausing about 1 second between each measurement, but you can continue to see now I'm at 3 volts, and the regulation error is now, it continues to go up, and I go all the way up to 4 amps. So I'm characterizing this from 1 volt to 11 volts, anywhere between 0 to 4 amps. So it's going to run, and it's going to finish, it's going to give us a table, and then we can look at the table in 3D actually and get a really nice view on the performance of the regulator. And at the same time, of course, everything is running here. I don't have to touch anything, I don't have to modify anything. Again, this is the power of the scripting capability of these units that allow us to do these tests very easily. And then if I want to change something, if I want to run it at a different range or different set of currents, all I need to do is to go in the program and just change 1 number or 2 numbers, because the code is already written. And again, as I said before in the previous review, this doesn't need to be connected to the computer. You can load the script directly through the USB, and they're all connected. You can have multiple units all connected together from one location and run it. You don't even need a computer. So let's go ahead and let this thing run, and when it's finished, we can take a look at the result. One other thing I wanted to mention is that the 1 second pause between the measurements is what I have chosen to ensure that the regulator and the capacitors that are the output of the regulator is stabilized. The units themselves can sweep much faster, of course. This is not a limitation of the instrument, but rather what I programmed into it. And it's important to make sure that whatever circuit that it is that you're testing reaches a stable point before you take a measurement. Otherwise you're measuring transient effects and not truly the IV characteristic. Here we're going here towards the end, and you can see at the end, even though the desired regulation voltage is 10.5 volts, we have a huge regulation error of 1.8 volts. It's because the circuit can no longer keep up, and one of the main reasons is because the op-amp is actually beginning to saturate. At the very top you can see the voltage coming out of the op-amp, and of course this is not a rail-to-rail op-amp, so it is not able to go all the way up to 12 volts, and even if it did, it probably have to go even above that in order for the transistor to turn on sufficiently to provide the current that is needed. So here you can see that the regulation is just crazy huge, so this is not really usable at the very high end. But we will be able to really appreciate how that works by looking at the plot in 3D, because it's so much easier to visualize. So here's one way to visualize the data we just collected. I just took the data directly from the script, which is right behind this window. Actually, this is the script that I had written for this test. Again, it's really straightforward. I'm not going to go through it, but it's very easy to catch up with this programming language if you've never used it before. So if I go back to the plot here, you can see that this plot is of course in 3 dimensions. On this axis right here, I have the regulator set voltage. This is the voltage that I am setting the regulator to, that I expect the output voltage to be. Here I'm plotting the regulator current. This is how much current I'm drawing from the regulator, and at the left side here is the actual measured voltage of the regulator. So an ideal regulator would keep its voltage constant no matter what the current is. Of course, this is not the case, and we're going to have some voltage drop depending on the amount of current. And you can see a trend where the surface dips down in that direction, and that's because in this direction is the direction of increasing current. Now, this might be a little bit difficult to appreciate on this plot by looking at it, but you can already see a little dip here where the regulator begins to suffer dramatically. This is an easy way to see it. You can see that it drastically drops in voltage as the regulation current increases, because it cannot keep up with the desired voltage. So instead of plotting it like this, what I can do is I can plot directly the regulation error, which I've done in this plot. This is much easier to understand. Again, on this plot is the set regulator voltage, on this plot is the set regulator current, and here is the regulation error in volts. This is how off the regulator is from the voltage that it's supposed to have. So for example, at very low currents and low voltages, from let's say 2 to 4 volts, the regulation error is very, very small when the current is about 0 amps. So at 0 amps, the regulator follows almost perfectly the voltage that it is set to. As the current increases, you can see the regulation error will go up. So if you look at this plot and say, well, where can I use this regulator? Well, you can pretty much use it in this flat region. Anywhere that is deep blue in color, the regulation error is less than, let's say, 250 millivolt. That may not be good for your specification, but let's say if your specification allowed 250 millivolt of offset, then you could use it here. And as the voltage increases here, even though in this region of the graph I'm not actually taking any current, the regulator is not able to follow the set voltage because the op amp saturates. So you can see that the error goes up. Now the error goes up much more when I expect the regulator to provide some current. And all the way up here, when I'm requesting as much as 11 volts and 4 amps, it's already off by 2.7 volts. So it's completely unusable in this region. But here's a very quick and easy way of characterizing a regulator. It doesn't have to be, of course, a voltage regulator. It can be a whole bunch of other different things, but really simply by writing a code between two source measure units from Keithley, you can get very quickly these type of plots. Again, I'm plotting this in MATLAB, not in the Keithley's ecosystem, but I'm just grabbing the data and dropping it into an array in MATLAB. This literally took just a couple of minutes to do. So this is one experiment that I wanted to show you, showing the scripting capability and also data visualization that comes out of the TSP. So let's go to a different experiment. Here's the setup for our next experiment. Here I have put together a temperature controller, and I'm going to explain to you how this setup works. So in between these two heat sinks, the bottom big copper one and the top black aluminum one, is a Peltier cooler. A Peltier cooler is a thermoelectric pump. By putting current through it, it's able to move thermal energy from one surface to the other surface. That's why it's called a thermoelectric pump. Depending on which orientation the current is pushed in or out of the terminals, it moves heat from one side to the other or vice versa. So therefore I can make one surface of it cold and one surface of it hot. Now what I've done here is that I've connected the bottom surface to this bottom heatsink, and this heatsink is used to exchange heat with the ambient, with the air inside the room, and there's a fan on the side to blow air through it. On the other side is the side which I'm interested in controlling the temperature of, and on there I have two thermocouples. One thermocouple, the one on the right, with the one that has the white cable coming out of it, goes into this Fluke 51.2, which is just simply here to measure the temperature of the heatsink independent of my setup. You don't really need this for this, it's just for a visual inspection. I'm using two type K thermocouples, and the ambient temperature is 25.5. It's pretty warm here in the lab right now. And the other thermocouple goes into our source measure unit. So by measuring the temperature with one SMU and controlling the current with this cable through the thermoelectric pump to the Peltier cooler with the other SMU, I'm able to build a temperature controller. Of course, it's not as simple as that because I have to program the algorithm in order to do the temperature controller, and I've done that by using a PID controller. Now, because I'm running a script on the source measure units, writing a PID controller is really straightforward. But there is also more to it than that. Because as you can see here, between these two source measure units, the bottom, the Keithley 2450, I have directly connected to the thermocouple. Now, the source meter isn't designed to measure temperature directly from a thermocouple, so I have actually programmed the polynomial that is used to convert between the measured voltage of a thermocouple to a temperature as part of this script running on the 2450, and I have programmed the PID controller, which controls, of course, the current with respect to the measured temperature and the error between the desired temperature and the actual current temperature into the 2460. Of course, this runs simultaneously on both units at the same time. But the job of the 2460 is to run the Peltier cooler, and the job of the 2450 is to measure the temperature using the thermocouple. Of course, the purpose of this experiment is not to suggest to use two source meters to build a temperature controller, although you could, and in some situations you may want to, depending on how specialized your temperature controller needs to be. But this is really to show you how flexible, again, these units are with this scripting capability to pretty much build anything you want. I mean, here I've built basically a thermocouple measurement unit and a PID controller directly into here, and it took me about maybe 20 or 30 minutes of coding to do that. So I'm going to to go ahead and run the code on the computer, and then I've actually programmed it to ask the user what desired temperature it wants to be. Now, because these are 4-quadrant instruments, I can set the temperature above ambient or below ambient. It doesn't matter because the instrument can both sink current and source current in any of the quadrants of the IV characteristics. So therefore it can actually jump back and forth between cooling and heating, and it actually will display that for us, which is one of the very convenient features of having a completely 4-quadrant unit. So let's go ahead and do that. First I'm gonna just turn this guy on. That's our fan that runs the little fan that runs the heatsink underneath to make sure that we have at least one of the heatsinks at ambient temperature. So let's go ahead and run the code. I'm gonna just initiate that from here. There we go. So at the bottom here is just now waiting for me to do something. It has a default temperature of 22 degrees Celsius, so I can go ahead and give it any temperature I want. Let's go somewhere well below the ambient to see the cooling capability. I don't know, let's try maybe 10 degrees Celsius and go okay. And there it is. So now you can see it's starting to do something for us. So at the top here it says that the set temperature is 10 degrees Celsius and it's right now sinking minus 2.5 amps. So it's trying to cool it really rapidly. At the bottom you can see the temperature quickly dropping and its state is in cooling. So it's now currently cooling as fast as it can, and it may overshoot, and I think it will. Once it overshoots, it may briefly actually hit heating. You can see it's still, oh no, it never reached it. I think it's smart enough. I think that I chose the coefficients of the PID controller reasonably well, so it doesn't have much of an overshoot, but it's going to go up and down for a bit. And again, because these scripts are running, the instrument is fully responsive. You don't have to, you're not limited, you're not stuck on these screens. You know, I can just swipe and then swipe up, and then I can see the curve, you know, the trend and so on follow. You can see that the current is now continuously going higher and higher. And if I wait long enough, eventually it's going to start coming back down. This is a part of the PID controller, which is, I haven't chosen the coefficients perfectly, so there's a little bit of overshoot and undershoot. But like I said, because the unit is running this script in the background, it's completely responsive, and I can press home again and it will bring me back here. So if I go to the right, you can see, so now we can see pretty much we are stabilized. You got 9.7 degrees Celsius. So if I touch that, it's if I touch the heatsink, it's quite a bit below ambient right now, and you can see the temperature at 10 degrees Celsius. So it's working really well, and it stabilizes fairly quickly. Again, the stabilization rate simply depends on the ambient coefficients in the PID controller that I've chosen. But you can see how easy and quickly you can put together a complex circuit. Now, I have limited the current here to 2.5 amps, but this guy can give me 7 amps at below 7 volts, so I can really easily cool things really fast or as slow as I want to. You can see right now the state is still in cooling mode. So it's going to basically reach a steady state current, which is going to be about 1 amp, where it can keep the temperature for me constantly at 10 degrees, and it's well below the ambient. I can go even lower if I want to, and eventually I can actually create frost on top of this condensation, which will eventually freeze once I go below 0 degrees. I did that before, but then you have to clean up the water that's going to start running off of this. But you can see the temperature is now perfectly set to 10 degrees Celsius, so it's working really nicely. So I went ahead and changed the coefficients in the PID controller a little bit more aggressively to show you what happens when it's a little bit more unstable. So this time let's go much higher temperature. Let's go well above ambient at 40 degrees. Again, I don't have to change anything in the setup. I kept the code exactly the same. I just changed the coefficients to demonstrate this interesting effect to you. Here we go, we're gonna go okay. And you can see that it's going to start heating because it needs to reach 40 degrees Celsius. Right now it's at about 31, so it's rapidly heating. It's maxed out at 2.5 amps. That's the current limit that I've set it. And as soon as it hits 40, it's going to overshoot 40. You can see it's now at 42 degrees, and it's going to rapidly jump down. Look, now it's cooling. So it flipped the current on the thermoelectric cooler in order to be able to bring the temperature down more rapidly, as if you were to just turn off the current. So this is much faster in cooling it down than if you were to just turn off the current. And now you can see, again, it overshot, it became too cold again, so now it's going to go back and forth. It's going to do this until it eventually stabilizes. And that's a very typical thing from a PID controller. By choosing the coefficients, if you don't choose them very carefully, you're going to get this issue. And it's going to do this a couple of times until it cools down, and I can go ahead and again look at the curve. It does a little bit of a strange thing sometimes. It draws this line across, which I'm not 100% sure why it does that, but it goes away after some time. I think this might be a minor bug in the drawing algorithm there, but I'm sure they'll fix that. You can see it is recovering back up, and then eventually it's going to come back down. So this curve is the second order time constant of the PID controller's response. So it's a very, very common thing to happen if you don't design it carefully. And if you go home again and if you go to the left, you can see that it's almost now sitting at 40 degrees Celsius, and maybe wait a little bit longer just so you can see, jumping between heating and cooling. But it's pretty straightforward and really fun thing to play around with, and you can program all kind of fancy and interesting things like this. So let's go to our next experiment. So as our last experiment, I'm going to characterize the saturated output power of this mini circuit's PA. Now sometimes you want to do some measurement across multiple instruments, and you can write a script to communicate with each instrument individually and collect data and process them, and that's perfectly fine. But if you want to develop something really quickly, you can actually use the data collection capability of the Keithley source measure units in order for you to enter data that you've measured from a different instrument manually on the screen, and then that instrument would then collect all of that and then give you a report at the end, nicely formatted from the script running. So for this experiment, I'm going to use 3 different instruments. On the left here, I have the Keithley, I have the Rigol DSG3060, which is going to be the synthesizer providing a single tone at a fixed output power to the PA, and that's going to saturate the PA at all times. And then in the middle, of course, I'm going to have the Keithley 2460 and the Keithley 2450. Now, even though I'm not using the 2450 to power anything, I can use its screen real estate as the input mechanism, and that will become clear in a moment. So the script is going to ask the user to enter the measured results here while simultaneously providing the voltage and measuring the current to the PA itself. And here on the left, on the right, I have the Tektronix MDO, which is going to be used to measure the saturated output power of the PA directly, and there's going to be a tone appearing there when the PA is turned on, and then that's going to be our saturated output power that we can measure. Now every time I measure saturated output power, this instrument, the 2450, is going to ask me for what that value was. I'm going to enter it, and when the sweep is complete, it's going to provide me with a report of all the measured results nicely in a formatted table, which then I can plot and analyze after. So let's go ahead and run the script. And here we go. So now you can see that the instrument is applying 5 volts and is measuring the current consumption. And at the same time, I can go over here and take a look at the MDO, and you can see that the MDO is showing the saturated output power about minus 4.4 dBm. So I can go ahead and now enter that value into the bottom SMU, which is a 2450. Even though it's not part of the measurement, it's only this one, I can use it as a data collection. So there you go, we enter minus 4.4 minus 4.4 minus, there we go, dBm. Okay, now it's going to advance to the next point. So now it's doing 5.5 volts. It's asking me again. Now the power consumption has gone up significantly, and also the output power has gone up significantly. Now it's about 0.8 dBm, and so on. Now it's at again advanced to 6 volt. The power now, you can see that the output power has gone up to 3.5 dBm, and this can continue up. Now it's at 6.5 volts. I can see the PSAT has gone up. Now it's about 5.5 dBm. So we can go ahead and continue to enter these values, and I'm going to do that and finish it off, and we will see the result at the end. Alright, that's the last one at 12 volts when the power, now the PSAT is 14.3 dBm, and there we go. And now it's finished, so it automatically turned the power off, and now it has provided a plot on my computer, which is all the results collected. So let's go and plot it and see what it looks like. And here's our plot that I've plotted in Excel actually for, you can see very quickly I can produce this. And here's the measured DC power. This is the power that's collected by the instrument itself, and this is the power that I entered, which is the PSAT. And you can see this curve, and it's interesting to note that going from about 1 watt to 1.4 watt gets you very little PSAT. So it would be interesting to investigate, based on this curve, what is an optimum biasing condition if you want to have a reasonable DC power and a reasonable PSAT, a compromise between the two, because this curve flattens out very quickly. So consuming more power at the very top here will not buy you much PSAT, whereas if you're in this region of the curve, of course, giving more power to the PA will give you much more PSAT. Remember, every 3
dBm here, you double the output power. So here, you know, maybe between these 2 points, you may be better off just saving some power and having a little bit less of PSAT. And I just want to show you this as a last experiment so that you can see how you can use the data collection capability and save you some time and quickly develop plots like this without having to program multiple instruments at the same time. Well, I hope that you enjoyed the review of the Keithley 2460, and I can of course make more and more experiments, but hopefully this provided you with a nice overview of all the diverse and interesting set of things that you can do with these two units. And if you enjoy these videos, please just take a few seconds and rate them. It really helps the channel to have good engagement between the audience and the videos that have been posted. And if you happen to purchase one of these because you saw the review on the signal path, let Keithley know about that. I get no portion of the profits. It's just so that I can have a good relationship with the manufacturer and continue to bring you videos in the future showing you new and interesting instruments as they come to the market. And of course I enjoy making these videos for you guys. So just keep watching the channel. There's a lot of other interesting things that I have planned for the future. Man, I'll see you next time.